Hello and welcome to this short introduction to Phyre. I'm Lawrence Kelly from Imperial College London and the chief developer of the Phyre web server. So what is Phyre? Well, essentially it takes a amino acid sequence that you've submitted to the server, you've pasted it in, and it will generate hopefully a three-dimensional model of your protein. This is what the primary Phyre submission screen looks like. We have a section to put your email address in, an optional job description, and a box to paste your amino acid sequence in, and then you simply click the Phyre search button here. So how does Phyre2 work? To start with, your user sequence here, shown in orange, is processed by scanning it against a large database of approximately 10 million known sequences to try and detect evolutionary relationships to other protein sequences, or homologs, using the program PsyBlast. We then gather these homologous sequences and can convert them into a hidden Markov model. This hidden Markov model captures from this alignment of sequences here the patterns of mutation that occur in your protein sequence across evolutionary time, and as such this hidden Markov model acts as a sort of evolutionary fingerprint of the evolutionary history of your protein. Meanwhile, we know of 65,000 currently protein three-dimensional structures. We can create evolutionary fingerprints for each of these as well. So we take a protein structure, extract its sequence, and process it in the same way as the user sequence by running PsyBlast, gathering sequence homologs, and generating a hidden Markov model, but this time of a known structure. We can repeat this for all of the known 3D structures to generate a large database, which we'll call the hidden Markov model database of known structures. So back to the user sequence, once we've generated one of these evolutionary fingerprints for your sequence, we can scan that against our database of other hidden Markov models to detect high confidence similarities. This scanning procedure generates an alignment between your sequence and a sequence of known structure. And this alignment permits us to generate a three-dimensional model of your protein. This entire technique is extremely powerful and it's able to detect extremely remote homology, even being able to create very accurate models when the sequence similarity between your user sequence and a known protein structure is even less than 15%.